This is Mrs. O'Neill for AP Chemistry, Chapter 11, Section 4, Phase Changes. You should have watched the intro lesson, Energy Changing Processes. These are my notes. He first compared Seattle to Bozeman, and that's where these Bozeman science video titles come from, because that's where he is actually from. They're both the same distance from the equator, but he wanted you to pay attention to the average high temperatures in those two places. And of course, he said that Seattle is more temperate, where Bozeman fluctuates more. It has a bigger difference in temperatures, and that's because of that Pacific Ocean releasing heat during the winter months and consuming heat during the summer months. And he reminded you that water has a very high specific heat, which he talks about a little bit more in detail later on. Gives you a nice flow chart as always. And then he did that PhET simulation where if you add heat, you're really adding energy. So then he said, well, look at these two beakers. One is 1 degree Celsius and one is at 25 degrees Celsius. Which one is going to have more energy? Of course, the warmer one. So then he represented those energies with these little E squares all over the place. So of course, the 25 degrees Celsius beaker is warmer. It's going to have more energy in those molecules. Well, what happens when you put a warm object next to that cold object? You should already know this. Energy, heat, flows from warm to cold until there's a thermodynamic equilibrium. So again, here you see the two beakers of water. They've come close together, and now their temperatures are closer together as well. He did a time lapse where ice melts, and then of course he went backwards. Again, if you need to pause the video and reread this information, that's fine, but that's basically what he was doing. As the heat was adding to the system, it melted the ice, and of course vice versa. Then he talked about different specific heat capacities of different substances. Gold is very, very low. It doesn't take a lot of energy to heat up gold on any time. Where water, it's going to take a lot of heat energy, 4.186 joules per gram degree Kelvin, or I shouldn't say degree there, Kelvin, in order to raise its temperature. And that's one of the reasons why pool water takes a long time to heat up. It takes all summer until it actually gets warm. So water is going to change the least amount because it has the high specific heat. It's going to take a lot more energy to change its temperature. So, of course, solid to a liquid to a gas, you have to increase the temperature in order to do that. So low temperature, medium temperature, and then, of course, high temperature. Then he talked about this heating curve, and that's one of the main reasons I wanted you to watch this video, is to get you to understand that these flat lines here, the two flat lines, one is going from a solid to a liquid, and the other one's going from a liquid to a gas. At that point, the temperature actually stays the same for quite a while until it goes into that other phase. And that's because adding energy doesn't necessarily mean that it increases the temperature. They require a certain amount of energy in order to switch from that solid to liquid. So here we have that heat, okay? We're adding heat, so that ice is melting, melting, melting. But then once it gets to a certain point of 0 degrees, I should say, this would be negative, not 0. Once it reaches 0, at 0 degrees, it's going to be in solid ice and liquid water until there's enough energy in that piece of ice to push those molecules over the edge and to raise its temperature above 0 degrees Celsius to get to liquid water. Okay, so we have ice at the negatives, 0, 0, 0, 0, 0, 0, until enough energy is added to push those molecules to the edge. So we want to remember the words fusion and evaporation. So fusion is really your solid to liquid, and evaporation is your liquid to gas, or vice versa. And this should make sense to you, right? That delta H. Positive sense, right, would be exothermic, and negative sense would be endothermic. And then he gave you those phase diagrams again, or I should say the exothermic reaction energy diagram. And this, hopefully, look it over again. You should understand this information, but it's good to review because this diagram is very, very important. So he gave you an example of exothermic. Again, if you need to pause and make sure you understand or review this information from Chapter 5, do so. And he also gave you an example of an endothermic reaction. Again, make sure you understand the energy diagrams. So onto your notes packet. Again, I suggest pause the video, fill in the blanks, and then play to hear my words. So in this section, you're going to explore these phase changes. In other words, the transitions between the gas, liquid, and solid phases of a particular substance. And again, that they're associated with energy. It's all back to that energy, and more specifically, heat energy. Familiar weather events can remind you that water exists on Earth as a liquid, a solid, and a vapor or gas. A spring shower brings liquid raindrops, and a winter blizzard delivers solid snowflakes. On a humid summer day, you may be uncomfortable because there is a high concentration of water vapor in the air. As water cycles through the atmosphere, the oceans, and Earth's crust, it undergoes repeated changes of state. In this section, you will learn what conditions can control the state of a substance. So let's look at these phase changes. As a matter of fact, if you could, I would pause the video, think of the term that would be used going from a solid to a liquid and solid to a gas and so on, and see if your words match mine. Did you get all those? Probably, if not half, a little bit more than half, but some of them you might not have heard of before, like deposition. That's a different word. And you want to think here freezing or precipitation is kind of like the same thing. So here's some examples. Again, pause the videos. Can you come up with an example of each of these on your own and then play and see if your examples are similar to mine? So did you come up with some of those? This says water to ice. I know it's in yellow. I was trying to make a neat little rainbow if you haven't noticed. Anyways, so those are examples, and maybe you have even better ones that you'd like to share. So just as a reminder, as we go from solid to liquid to energy, as we're absorbing that energy or adding energy, no, I'm sorry, I shouldn't say adding, right? Well, yeah, adding energy to the system, where the solid is going to turn to a liquid, that's going to be endothermic. All of these red lines going up are endothermic, and the blue lines coming down when they're releasing energy to the surroundings, going from a gas to a liquid to solid, it's an exothermic process. So again, you've seen this before, but now those are those change of phases terminology that's in there, and that's something that you might want to draw out, because this, again, this chart, this graph is really important to understand as we go from solid, where the atoms are real close together, and we're separating them out, right? That's really what we're doing. We're pulling those atoms farther away from each other. So those atoms that in a solid have to absorb energy in order to break free or break apart, right? We're breaking, and I want to put those in quotes, right? We're not really breaking those atoms, but we are separating them farther apart. Same thing when we go from a liquid to a gas, right? We are separating those molecules or atoms further apart, kind of like breaking bonds, and that's going to be endothermic. So then obviously going down or releasing energy would be the opposite, and that would be exo. Here's another just neat graph. Again, if you want to draw it this way, or it gives you that nice visual and all those words that you need to know. So what is evaporation or vaporization? Same thing, right? Energy required to take that liquid and put it into the gas phase. So there's that heating curve that he talked about. Again, we need to understand you're going to be here at 0 degrees for water. Now, every substance has its own melting and freezing point. So for water, it's going to be 0, but it's going to be 0. That piece of ice is going to be 0 until it has that certain amount of energy to push those molecules, push those atoms from that solid to a liquid phase totally. So that's called a plateau, sometimes they call it. So again, we have the solid phase, solid liquid phase, liquid gas phase, and then of course your gas phase. So again, when we're adding heat, we're adding energy, and we're trying to get those molecules to go into a new phase. Here's your heating curve again, just to make sure you're understanding. Let's look at for water. There's ice and water, there's water and steam, and there's steam or vapor. So guys, this graph can be for any substance. Of course, the different temperatures would be different, right? So the for water and ice, it's 0 is your melting and freezing. For boiling point, it's 100, but for other substance, of course, the graph would look similar as far as the shape, but the different temperatures, those plateaus would be at different temperatures. Those are the slopes for the heat capacity, so how much heat is needed for that liquid to turn into a gas. Okay, that's your heat capacity, how much heat is being absorbed. We want to remember that that's fusion, right? We always want to talk about solid and liquid being fusion, and up here would be vaporization. Again, liquid to gas, evaporation or vaporization. It's the same words. See you in class.